A major highlight of my work package was that we developed and demonstrated a novel 2-qubit gate based on Landau-Zenner-Stückelberg interference. By modulating only the tunable coupler, we achieved fast, continuously tunable gates while keeping the qubits isolated from spectator errors. After characterization at KT, the gate was successfully deployed on the QSolid demonstrator in Forschungszentrum Jülich with measurements by crews and strong support also from our partners in Jülich. This cross-stack collaboration marks an important step towards scalable, modular superconducting architectures in Germany.
Within QSolid, we successfully developed a fabrication process for superconducting aluminum air bridges and their integration onto our qubit wafers. This enables, on the one hand, electrical grounding over the structures and also signal routing between different parts or different structures on our qubit wafers or qubit chips. And with this, we can build more complex structures for the QPUs because they are no longer limited to planar thin film technologies, and we can help scale up the numbers of qubits on a chip, which is pretty fancy.
One important outcome of my QSolid work package was the evaluation of our fabrication technology to fabricate now novel quantum processor units. We started from our chipwise fabrication and now are able to fabricate the nanoscale qubit structures on a wafer, and we achieve very small parameter variations of less than 7% across the wafer and less than 3.5% in the central area of the wafer. This gives us now the chance to focus on making the qubits better and also to check for reproducibility, as this is required for our final goal to offer it as a foundry service for partners from industry and also academic partners across Europe in frame of the Fluxonics Foundry.
If we want to scale qubit numbers up, we face a critical bottleneck, and that is the wiring feeding the signals in and out of the cryostats, which is a mechanical and thermally challenging problem to solve. So in QSolid, we research in parallel cost-effective room temperature electronics as well as cryogenic electronics alongside thermally isolating superconducting interconnects, which brings us one step closer to realizing a fault-tolerant quantum computer.
So the theory contributions came from all around Germany. The group in Berlin introduced a novel decoding technique for quantum error correction. In Munich, IQM developed an advanced error mitigation framework. From Ulm, we gained a powerful noise simulation toolbox. And in Constance, we achieved a better understanding of correlated noise and how it affects quantum hardware. So all these contributions collectively push quantum computing towards a fault-tolerant reality.
Work Package 8 is where optimal control theorists, control electronics manufacturers, and firmware developers came together to make sure quantum computers can have really high-fidelity gates and operations. This allows the end users to be able to run algorithms that can give them some value and advantage, and this was really great within the project.
When I think about the past project years, the highlight of our work package is seeing how research is transformed into application across different levels of system architecture. We start with a simple question like, what is a good use case for a quantum computer? Then we develop error mitigation techniques on an algorithm level. This is followed by an optimized compilation for the given quantum chip. We see our work package as an interface between the global users and the hardware built within this project.
In work package 10, we connected the quantum computer to end users. And it's not just a quantum computer, it's a quantum computer integrated in a high-performance computing environment. And what's really special about this project is that so many things came together. A quantum computer is sensitive to so many little things that you're not used to when you think of classical computers. So we had a long learning process that's now starting to produce its fruits. We tried to figure out, we had now the computer up and running for some time, and we learn each time new details about what we can connect better, how we can avoid certain influences that we want to avoid. There's so much that we learned right now, and we still want to continue to build on that.
System engineering and system integration were very important for the realization of a complex system like QSolid. They are about getting the right element with the right quality at the right time to the right partner. All the partners got on board, and we did it.